Welcome to CSAI Think Tinker Learn. Today, we are entering the big leagues of infrastructure as we explore load balancing and physics of scale. This is part of a new System Design Essential series, where we cover architectural pillars at a high level to help you build a solid mental model quickly. Before we jump in, please take a moment to hit that like button, share this video, and subscribe. It really helps the channel grow. For deep dive article and visual guide, visit our companion site at um, here. The link will be in the description as well. The articles are listed here. This is a work in progress site, so as and when we develop more articles, we'll be adding them here. All the articles which are hyperlinked are available for reading. So now coming back to the videos. These videos that in the series of system design essentials are designed to be concise. But if you want a dedicated session on something very specific or a deep dive onto something, like math behind consistent hashing, let us know in the comments. Remember, at scale, physics beats your code. You can't just make a worker faster. You must distribute the work. Let's see how. Every engineer eventually hits the vertical scaling wall. You can buy more RAM and a faster CPU, but hardware upgrades yield diminishing returns. More importantly, a single massive server is a catastrophic single point of failure. If that one motherboard or CPU saturates, the entire application dies. CPU thread limits, RAM session exhaustion, NIC physical bandwidth, and disk I/O contention are the physical boundary that force us towards horizontal scaling. Stop trying to build a supercomputer. Start building a fleet. The first decision is where to inspect traffic, layer 4 or layer 7. Layer 4 is an inspection station that is blind but blisteringly fast. It makes decision purely on network metadata like IP address and port. Layer 7 is smart. It has full visibility into HTTP headers, URL paths, and cookies. While layer 7 allows you to route /API/payments to a different cluster than /API/images, it costs significant CPU cycles. Misusing layer 7 for high throughput raw data stream is a classic way to exhaust your load balancer's resources. Stateless engines like round robin or random distribution are the simplest tools in the shed. They distribute traffic blindly with zero overhead because they have no memory or past requests. However, they fall into a heavy job trap. If your workloads vary in sizes, like a tiny JSON fetch versus a massive video transcode job, naive algorithms will accidentally bury one machine while others stay idle. These algorithms require a perfectly homogeneous server fleet to be effective. Stateful engines like least connections are more intelligent. They track active connections in real time to route traffic dynamically to the emptiest tank. This is perfect for variable duration requests, but there's a catch. It requires shared memory and state tracking across the balancer. Without strict locking, you run into race condition where concurrent incoming requests read the same minimum value simultaneously and flood a single server anyway. Tracking state always has a performance cost. The Modulo Math Trap is a senior engineer's nightmare. You might think using hash IP%n or modulo n is a clever way to ensure a user always hits the same server. But if you add or remove a single server by changing n, almost every client remaps to a new destination. This results in a shattered cache. Your database will suddenly face a thundering herd of cache misses as every server tries to rebuild its local state at once, usually leading to an immediate system-wide failure. The solution to modular trap is consistent hashing. We arrange servers and requests on a circular ring from 0 to 2 raised to the power 32. When you add a server, only the immediate counterclockwise neighbors shift. Everyone else stay put. To guarantee even distribution, we use 100 to 200 virtual nodes or replicas per physical server. Understand this slide and you'll pass 80% of system design interview. This is the exact mechanism that powers industry giants like DynamoDB, Cassandra, and Redis. Load balancers must prevent the black hole via health checks. Active checks involve continuous synthetic probing on a background loop, asking, "Are you okay?" Passive check monitor live traffic or 500 errors or timeout. A crucial tip, never pull a server after a single missed ping. Network blips happen all the time. Always configure grace periods and failure thresholds, like 3 consecutive failures, to prevent flapping, where a server is repeatedly joined and removed from the pool. State is the absolute enemy of scale. Sticky sessions, where the load balancer is forced to remember which user belongs to which server, breaks horizontal scaling, and create hotspots that are impossible to balance. True stateless routing requires moving memory out of the application tier and into ultra-fast external data stores like Redis or Memcache. When your application servers don't remember who the user is, your load balancer can do its job perfectly. We must guard the gate itself with high availability. Load balancer are SPOPs, or single point of failures. We run them in active passive pairs using virtual router redundancy protocol. The active node holds a virtual IP. If the heartbeat network line fails, the passive node takes over. However, watch out for the split brain scenario. If the heartbreak, I'm sorry, not heartbeat, heartbeat, if the heartbeat link is cut, both nodes are still alive, both will claim the WIP, causing catastrophic routing conflicts and data corruption. To beat the speed of light, we use GeoDNS. A user in Tokyo hitting a Virginia server suffers 150 milliseconds of latency just from fiber optic physics. GeoDNS routes traffic at the DNS level before it even hits a regional load balancer. The catch here is TTL lag. If a whole data center dies, clients with cached DNS records will continue to route into a dead zone for hours until their time to live expires. Localized failure can have a global impact if your TTLs are too long. The modern approach is client-side mesh. The load balancer is no longer a centralized box. It is pushed directly into the infrastructure mesh as an Envoy sidecar proxy. This requires service registry like console and control planes like Istio to constantly update the sidecars with healthy IP addresses. In this model, developers don't write routing logic. The infrastructure handles retries, circuit breaking, and balancing transparently at the source. Choosing an algorithm shouldn't be a guess. Use this selection matrix. Are your server homogeneous? If no, use weighted round robin. Are request durations highly variable? If yes, use least connections. Do you need routing consistency for a dynamic server pool? Then consistent hashing with externalized state is the only viable path. Don't use a favorite algorithm. Use the constraint of your data to dictate the architecture. This is the synthesis of production grade payload. Every layer independently solves a specific failure mode. Level 1, which is GeoDNS, solves geographic latency. Level 2, HA pair, solves gateway failure. Level 3, which is at layer 7, handles intelligent routing. Level 4, which is a stateless array, handles the bulk work. Level 5, which is at the Redis, handles the user memory. This layered approach is what a globally distributed, fault-tolerant architecture actually looks like in the real world. As we wrap up, remember these final directives. State is the enemy, so externalize it. Physics dictate latency, so route geographically. Everything will eventually fail, so build redundant pairs. And simple math breaks at scale, so use consistent hashing. Now, I have a question for you. Have you ever seen a sticky session cause a production outage during a traffic spike? Tell us your story in the comments. If you enjoyed this video into the networking layer, please like, share, and subscribe. See you next time.